Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at the favorability reaction using the reaction quotient. So this is going to be another way of looking at whether we expect a reaction to go in the forward direction or the reverse direction than the much more mathy Gibbs of reaction. So when we're looking essentially at trying to figure out how favorable reaction is, one of the most important things to remember is the equilibrium constant only tells you what the most favorable ratio of products to reactants are. It doesn't tell you where the reaction is at any given moment. So for example, let's look at the decomposition of dinitrogen tetroxide. In this case, our equilibrium constant is less than 1. That tends to mean that we're going to favor reactants over products. However, we don't know whether we have more reactants or products at all. So I need some sort of variable to tell me what the exact momentary composition of a system is. And that's where the reaction quotient comes into play. So the reaction quotient is going to take the same exact form as our equilibrium constant, but the key difference here is it's not going to use the pressures or concentrations at equilibrium. Instead, it's going to use the momentary or instantaneous concentrations. So one of the key things is if you have a Kc, you're going to want to make sure to use only molarities. If you have a K or a Kp, make sure to use pressures. So in this case, I've got the equilibrium constant as a Kc. So this is going to be the ratio of molarities at equilibrium of my products of nitrous oxide over my reactants. Now, one of the big things here is that this is going to be that ideal chemical ratio. However, Q is going to be that instantaneous. And the big thing is Q is going to want to become K. K is who everybody wants to be. However, sometimes you have too many products, sometimes you have too many reactants. And so the key trick here is going to be moving moles from one side of the equation to the other. And if I know the ratio in between K and Q, I can help tell which direction I need to move. So let's go ahead and start by looking at some extreme examples. So let's say I start with just reactants. So I put 0.2 moles of my dinitrogen tetroxide into an empty container. So at this point, my reaction quotient is going to be 0 because I have 0 product. So I have no quotient. You need product and reactant to make a quotient. So at this point, my value is very small. And I know that my Q wants to be equal to 4.6 times 10 to the negative third. It's too small, so I need to make more products. And this makes sense because if I only start with reactants, the reaction has to occur to some extent in order to get any sort of equilibrium. On the converse side, let's say I start with just products. So I start with 0.2 moles of nitrous oxide. Well, at this point, my reaction quotient is going to be infinity because I have no reactant, and dividing by 0 is a bad idea. So in this case, it makes sense the reaction is going to want to go in reverse because I have to have some balance of reactants or products. And this really helps illustrate an important point. You're almost never going to see a reaction that is entirely reactants or products, at least if it contains a gas or an aqueous species, because it's really going to mess with your reaction quotient. You're never going to have a K of 0, and you're never going to have a K of infinite. You can have really large Ks, you have almost no reactant whatsoever, and we'll see some cases of that. We're also going to see some very small Ks where you almost make no product, and we'll see some examples of that. So let's go ahead and try and figure out if I have an individual Q and an individual K, which direction the reaction will go forward in a more general system. So again, let's say that I have a K that is greater than Q. So I'm going to encourage you to always write the K on the left and the Q on the right. So in this case, if Q is small, it means that I've got too many reactants and not enough products. So we can make the reaction more favorable by shifting some of my reactants and turning them into products. This will make my Q larger, so it's more likely to be equal to my K. You can also see this by, again, look at which direction the arrow is pointed. If K is greater than Q, the reaction goes to the right. Look, the arrow already tells you the way. Now, in the converse side, if K is less than Q, the reaction will proceed in reverse. And you can see this because there's going to be too many products and not enough reactants. The value is too large. So to make it smaller, I have to beef up that denominator. And so it goes to the left. And so again, just by looking at the ratio of K to Q, the arrow tells you the way. But make sure you start with K first because K is lower in the alphabet, should come first. Now, if K is equal to Q, then we're going, again, as we saw last time, equally backwards and forwards. So no net movement happens and it stays put because there's no arrow, so we don't move. So this is a good shorthand for trying to figure out how things go. So if it's easier for you, use this kind of short mnemonic. If it's also easier for you, go ahead and look at, do we have too many products or too many reactants, and how do you get rid of them? So generally what we're going to see as a reaction proceeds forward, you're going to see that reaction quotient slowly change. So if I have a very large reaction quotient, such as infinity, because I start with all products, then I'm going to have to make more and more reactants until my Q slowly gets lower. And it's going to keep proceeding until Q equals K, at which point all reaction stops. And so one of the biggest advantages of using this reaction quotient is it tells you what direction a reaction can occur at any given point in time. And this is really important because in order to figure out what an likely equilibrium concentration is going to be, you need to know whether the reaction goes forward or reverse. Without that, you can't do much. However, next time we're going to look at a fun case where what happens if a reaction already starts at equilibrium and we muck about, add some products, reactants, heat it up, what happens? So next time we get to Le Chatelier. Until then, take care.